So as you're working through these, hopefully you remembered that when solving an absolute value equation like this, the first thing we do is we try to get the absolute value by itself first. So like in that first one, that means I'm trying to get that by itself, which means getting rid of the minus 10. So go ahead and add 10 to both sides. When you do that, you have the absolute value of x equals 36. Now remember the reason why we do this. Once we get to absolute value of x equals, I now have to split it up into two pieces. Because the absolute value of 36 would equal 36. But the absolute value of negative 36 would also equal 36. And so we have two different possible answers. In this case, since it's just absolute value of x, it's not absolute value of x plus or minus something, we go straight to that as our final answer. So your final results, x equals negative 36 and 36 there. Second one, same basic idea. We want to get the absolute value of x by itself first. Well, notice there's two things in the way here. We got the 4 in the way, and we got the plus 5 in the way. Which one do we want to get rid of first? Yeah, the 5, because it's the addition and subtraction. If you try to get rid of the 4 first, it technically can be done, but it creates a lot of headaches and has some special rules involved. So move the 5 first. When we do that, we subtract it from both sides. You got 12 equals 4 times the absolute value of x. Can you just distribute into absolute value? Like, could I just multiply the 4 in and turn this into like just 4x over here? No. We can't do that. We still have to get the absolute value by itself. And so that means moving the 4 out of that side and into the other side. So we divide both sides by the 4. Then we got absolute value of x equals 3. So x equals both negative 3 and positive 3. So this was just bringing back old work. This was bringing back the stuff that you've seen, that you've done, kind of re-engaging your brain, getting it ready to think about math again. But it's not our main focus today. Our main focus today is one of those topics that, again, for some of you is like, oh yeah, that's easy. And for others of you, it's like, I've never gotten this before. Well, then the good news is today you will. Because today we're taking a look at dividing fractions. So, write down this first problem. Fractions is troublesome for a lot of people. And so that's why I actually take a little bit of time here and there to review it. And partly because, as you've seen, we start dealing with some complicated looking fractions in here, right? And yes, we're going to be dividing them as well. All right, so how do we divide fractions then? And this is the one that often people will get a little bit mixed up. Sometimes people will say, is this where we cross multiply? No. Although some people will force that to work in its own weird little way. But we only cross multiply if this is actually an equal sign. If you have a fraction equal to a fraction, that's the one where you cross multiply. Division is the one where we multiply by the reciprocal, if you want to be all fancy and mathematical about it. By reciprocal, though, that's just a fancy math way of saying that you flip the fraction. And so, in order to do this, the first fraction stays the same. The first fraction will always stay the same when dividing. We then are going to multiply by the reciprocal, right? So notice I say multiply, so our division becomes multiplication. And reciprocal means flip the second fraction. So that becomes 6/5 instead of 5/6. So notice what I did here. And this has to happen. We did two things, and they have to happen at the same time. I changed the division to multiplication and flip the second fraction. We got to do that all at once. Now that I've done that, now you remember how to do this, right? Because now it's just multiplying. How do you multiply fractions? Yeah, straight across the top, straight across the bottom. So on the top then, I'm going to do 3 times 6, which is 18. Multiply straight across the bottom. 4 times 5. That's 20. Great. Are we done? No. We can reduce it, can't we?
Divided by 2.
Yep. We can divide everything on top and bottom in this particular case by 2. And so 18 divided by 2, that gives me 9. 20 divided by 2, that's 10. 9/10. Is that my final answer? Yes, it is. That one cannot be reduced any more past that. And we just got a single fraction as our answer. So yes, that is good. That is done. That's all we want for that. So 9/10 will be your final answer for that. Now, this might be a good time to think about notes. How do you remind yourself about this process? Because you can look at this work later and see what you did, but is that enough if you forget how to divide fractions? For some of you it is, but if not, maybe make notes to yourself. If you want to be fancy and mathematical about it, you could actually write multiply by the reciprocal. And so you could actually write that on your paper as a way to remind yourself about how you divide fractions. Or, that's a bunch of big words. Maybe we don't want that. So you could also write, for instance, get a different color here. You could write division becomes multiplication. And then flip the second fraction. Those are just a couple ways you could make notes to yourself about what we're doing here. Basically, you always want to have some way of remembering. If the work is enough for you, go with the work. But if it's not, because that often isn't the way that makes sense to you, write down some words. Do whatever you got to do to remember. All right, so I now want us to practice this idea. So go ahead and please simplify both of these problems. All right, so to do these, of course, the process is the same. Every time you see division with fractions, we got to think about multiplying by the reciprocal. So I'm going to flip the second fraction. So in this case, the 1/6 becomes 6 over 1. And when I flip it, at that point, it becomes multiplication. And now that we've gotten to the multiplication phase, we can now go ahead and do that multiplication. So it's straight across the top, 1 times 6, straight across the bottom, 3 times 1. We get 6 over 3. Does that reduce? Yes, it does. Now, when doing this, some of you are going to go straight to the answer because you're seeing it as 6 divided by 3. And that works in this case. But what if you don't see that? Well, what can you divide both 6 and 3 by? 3. So if we divide both top and bottom by 3, that ends up giving us 2 over 1. Anytime you see a number that's just over 1, it equals just that number. So your final answer then is 2. And so that is it. That's what I'm looking for there. It's just 2. All right, next one. Same basic idea. Flip and multiply. And that's going to be the big thing to remember. Flip and multiply. So it becomes 1/4. I flip, always flipping the second fraction. It doesn't matter which one's bigger or smaller. It only matters which one's first and second. Flip the second fraction and change it to multiplication. I now can multiply straight across the top. 1 times 8 is 8. Straight across the bottom, 4 times 3 is 12. And then look to reduce the answer. What can I divide both 8 and 12 by? 4, yeah. So I divide top and bottom by 4 here. 8 divided by 4 is 2. 12 divided by 4 is 3. 2/3. Does that reduce down any more past that? Nope. Therefore, that is my final answer. We are done there. We're going to keep practicing a few little variations, making sure there's no little weirdness that's going to crop up and trip you up later. So go ahead and now do these two problems, please. All right, so to do these then, our method is the same. We flip and multiply, always flipping the second. But in this case, we have whole numbers in there. So like 9 there. What's 9 as a fraction? Yeah, 9 over 1. And so really I'm treating this as 9 over 1 divided by the 3/5. And now that I've written it like that, it's the same kind of thing as what you're familiar with. So the 9 over 1 stays the same. I flip the second fraction, always the second fraction, and then we change it to multiplication. Do the work from there. 9 times 5 on the top is 45. 1 times 3 on the bottom is 3. I can divide top and bottom both by 3, which gives me 15 over 1, which of course is just 15. So that's it. That's your final answer for that first one. We got a whole number as it happened. That won't always happen, but sometimes it will. Second one, same basic idea. I start by turning the whole number into a fraction. So it becomes 3/2 divided by, because I'm not flipping it yet, 6 over 1. Now that I've gotten both as fractions, I go ahead and flip and multiply. So the 6 over 1 becomes 1/6. The division becomes multiplication. Remember, always at the same step. That's not two separate steps, or it can get you very confused. It's all one step. Then multiply straight across the top, straight across the bottom, and reduce. You should get an answer here of 1/4. All right, so now for these, again, same method. So I turn my whole number into a fraction. So 1 becomes 1/1. Now, I don't like to do two things at once because that can lead to errors, so I go ahead and just still keep it as divided by 3/4. Then I go ahead and do the flip and multiply. So I end up multiplying them by 4/3. Multiply straight across the top, straight across the bottom, you end up getting an answer of 4/3. Now, 4/3 is a top-heavy fraction. Does that mean we need to turn it into a mixed number? Well, not right now. We haven't dealt with mixed numbers in here, and I don't want to deal with something that we haven't actually talked through. I want to build up some of those skills. So you can go ahead and leave it as 4/3 right now. If you are feeling comfortable with your mixed numbers and you want to go that direction, yes, you could call it 1 and 1/3. That would be fine there. But 4/3 is also fine. All right, same thing for that last one, just to make sure that we got the whole process down, right? So we don't need to turn anything into fractions here because they're already fractions. So we got 6/5 times 2/5. Multiply straight across the top. 6 times 2 is 12. And multiply straight across the bottom. 5 times 5 is 25. Every now and then, that will trip somebody up. Because there is adding fractions. And when adding fractions, you have to have a common denominator so it stays the same. So sometimes when they're both the same, it'll trip someone up. So just be careful that since this is actually a division problem, not addition, we actually still have to do the multiplication here of 5 times 5 to get the 25. Now, does 12 over 25 reduce? No, it doesn't. And so then, that's your final answer. That is it. Now on to everybody's favorite, some word problems. The nice part is, though, that we've just been talking a lot about dividing fractions. So that already is going to give you some hints on what you might do in terms of approaching these. So, we got a road striping machine that can paint half of a mile of road with 1 can of paint. Alright, so we want to know how many miles can it paint with 20 cans. How would we write that mathematically? Well, we always start with what we start with. And what are they starting with? What do they have to start with that they're dividing up? Which number is it? So yes, we start with the 20 because they start with 20 cans, and that's what we're going to be divvying up here. Now, we want to see how far 20 will go if each one does half of a mile. Okay, so we know we got a half there. Now, it's kind of like I got that 20, and I'm cutting it up into pieces that are each 1/2 big. Cutting it up into pieces, of course, that tells you then division. And so that's how I'd know to set it up this way. Of course, you probably were just looking at it and thinking, well, we were just doing division, so I'm betting we'll do division, which would be a safe assumption here. But that's why. Because we're actually cutting it up into pieces that are each 1/2 big. And now that we're here, we can go ahead and do the math. And so to do the work, we make it 20 over 1 divided by 1/2, which becomes 20 over 1 times 2 over 1. So the whole thing ends up being 40. And so it ends up being 40. This is a story problem, so I usually look back at a story problem and see, do I know what that 40 actually means? And it's asking how many miles can it paint? So it's 40 miles. I'll actually include the units in there, include an explanation, because we start with context, so I want to end with it as well. Something that's kind of cool here too that you can see is you can see that because of this, notice that dividing by 1/2 is the same as multiplying by 2. So next one. In this case, we have a piece of wire that is 3/4 of a meter long. We want to cut it into pieces that are each 1/8 of a meter long. How many pieces will we get? So remember that when I write down my problem, when I write down the math part of it, I always start with what I start with. So what's the big amount that we're starting with here? The 3/4. Because the piece of wire that we start with, so we got some piece of wire here, it's 3/4 long. We're going to be cutting it up into pieces. So the 3/4 is that starting amount. All right. So I start with the 3/4, and if I'm going to be cutting it up, again, cutting means division. So we divide it then by the 1/8. And now from here, of course, it's just a matter of doing the math, right? So actually do that division so we have that practice, have that answer handy. And so we do the normal flip and multiply. And then we multiply straight across the top, straight across the bottom. 24/4 does it reduce? Oh yeah. I can divide top and bottom both by 4, which gives me 6/1. Of course, 6/1 just equals 6. Now, again, thinking about what are the units there, that's 6 what? Well, if you're not sure, go back to the question. How many pieces will we get? 6. Therefore, it must be 6 pieces. And so then that would then be our final answer. 6 pieces is how many we get out of that whole piece of wire. So then for our last one here, we have a tree that's been growing 1/3 of a meter taller every year. Sounds like about a foot, but we got to stick with the meters. It is now 9 meters tall. How old is the tree then? Assuming it's a consistent rate every single year. So what's the big overall amount that I'm like cutting up into pieces? Yeah, the concept of a starting amount can be a little bit deceptive in this case because we don't want to start with the 0 that the tree started at. I'm wanting to look at what's the big amount that I'm having to cut up into pieces. So that's like, I'm trying to figure out how long did it take for the tree to get to 9 meters tall. So then the total then is the 9. So the 9 will be the first number I write down. Yeah, it gets a little bit tricky sometimes. And that's actually the hardest part with these story problems is figuring out what we start with. And so I want to see if it goes by 1/3 every year, how many pieces did it get cut up into to get to that 1/3? And so we'll be able to do that math, so go ahead and do that math. And when you do that work, you get 27. Now that's 27 what in this case?
Years.
Yep. Again, you can always go back to the original problem where it said how old is the tree? Oh, okay, so it must be 27 years old. So it took 27 years to reach that. Now, if getting that set up was a little bit tricky for you, it might have been a little bit easier for you to think about it algebraically. Because you could have actually said, okay, what I'm really trying to do is take 1/3 times what, like my number of years, equals 9. And notice, in order to solve that, you'd have to divide both sides by 1/3. And you'd end up with the same kind of thing. So for some of you, that might be an easier way to think of it. It's usually not the typical way, like the most common way, but it is a very good way, because of course I love algebraic reasoning on these.